In the last period, my dear students, we have studied about the modern periodic table. Let us do a small revision about the modern periodic table. You can see here on your screen that as far as modern periodic table is concerned, uh, the modern periodic law says that properties of elements are the periodic function of their atomic numbers. So you can see here we have the vertical columns, which are called the groups, the horizontal rows, which are called the periods. We have total 18 groups. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 32, 18 groups. And we have 7 periods. You can see 1, 2, 3, 4, 5, 6, 7 periods. Each period has got some number of elements. That is why you can say that the first period has got 2 elements, second has got 8, third has got 8, fourth has got 18, 5 has got 18, 6 has got 32, and 7 has got incomplete. Now suppose you are given that if the atomic number Z of an element is 38, my dear students, so how will you arrange the electron? As we know that in the first period we have 2 electrons, then in second we have 8, and in third we have 8, and in fourth we have 18. So total it is 18 plus 18, that is 36. So in the next one you will put 2. This is how this number, the number of element present into the period, represents the shell or the number of shell in which you can fill the electrons. So my dear students, for any number of, suppose you have 59, atomic number Z is equal to 59. In that case, you can write it as a 2, 8, 8, 2, 2, 8, 8, 18, 18, and 32. Now you just need to calculate it that 10 plus 8, 18, 18, 18, 36, 36 plus 10, 46 plus 8, 44 plus 2, 46 plus 30, it is 76. So this is how, my dear students, according to that, suppose if you write for this, so this is what it gives us, total number, that is 18, then you have next 18. So if you have Z is equal to 59, you will have 2, then 8, and then 8, that is 18. Then you have 18, that gives us total 36. Then again you have 18, that 8 plus 6, 14 plus 1, 1 plus 54. Then again, then you need to add just 5 here. So for 59, the electronic configuration would be like 2, 8, 8, 18, 18, 5. So this is how, my dear students, we can write the electronic configuration for any element with any atomic number by using this number of elements present into the uh, various periods in a periodic table. Now, my dear students, we want to study about the activity 5.6 from your textbook. So you can read this activity even in your textbook. I have just tried to solve this activity. How do you calculate the valency of an element in its electronic configuration? So to calculate the valency, the first step is look at the outermost electron called valence electron. If valence electrons are 4 or less than 4, then we can say less than or equal to 4, then valency is equal to number of valence electrons. Now if the valence electrons are more than 4, my dear students, then my dear students, we calculate the valency is equal to valence electron minus 8. Now this is how we can calculate the valency for using the electronic configuration. Now second, what is the valency of magnesium with the atomic number 12 and sulfur with the atomic number 16? So magnesium, your Z is equal to 12. So according to the electronic configuration rule, in K 2 electron and 8 electron and M 2 electron, so it is 2, 8, 2. So you can see that 2 is the valence electron. So valence electron is equal to 2. 2 is less than 4. And if the number of valence electron is less than 4, my dear students, valency is equal to number of valence electron. And that is why here the valency of magnesium is equal to 2. Same way, my dear students, look at this and understand it. Activity 5.6, find out the valencies of the first 20 elements. So here we want to find out the valency of first 20 elements. See, I have written the atomic number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. The name of the or symbol of the elements: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Their electronic configuration is 1, 2, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, 2, 8. For each electronic configuration, I have underlined the valence electron with the red pen. You can see now the valence electrons are here. In case of hydrogen, it is 1, helium 2, lithium 1, beryllium 2, boron 3, carbon 4, nitrogen 5, oxygen 6, fluorine 7, and neon 8. Now we just need to find out, or we just need to understand whether these valence electrons are greater than 4 or less than 4. So here you can see that up to this, up to all this, like from if you started from hydrogen to the if you start from the hydrogen to the carbon, the number of valence electrons are all less than 4, and that is why the valency is equal to number of valence electron in this all these cases. But when it comes to the nitrogen, oxygen, fluorine, and neon, the number of valence electron is 5, 6, 7, 8 respectively, and that is why the formula changes, because all these valence electrons are more than 4, and that is why the number of valence electron or valency is equal to number of valence electron minus 2. Now here helium is a special case. Helium is the inert gas, and the first shell, which is known as the K shell, where maximum 2 electrons can be filled, and that is why this K shell is complete in case of the helium, and that is why its valency is considered to be 0. This is what you need to remember, that the helium has 2 valence electrons, but its valency is 0, because helium is an inert gas and its first shell, that is K shell, has been completely filled, and that is why the valency of helium is considered to be 0. Now when it comes to the nitrogen, oxygen, fluorine, and neon, nitrogen has got 5 valence electrons, so the valency is minus 3. Oxygen has got 6 electrons, so 6 minus 8, it is minus 2. Fluorine has got 7, so it is minus 1. And neon has got 8 electrons, so 8 minus 8 becomes 0, because it is the inert gas, and all the inert gases have the valency is equal to 0. Now, my dear students, as this minus and plus sign is concerned, please remember that valency cannot be minus or plus, but here I have put minus or plus sign because you can understand that what kind of ion they are going to make. So here you can understand that nitrogen will make N minus 3, oxygen will make O minus 2, F will make F minus 1 ion, and this is how you understand. So please do not consider this negative sign as a valency. Actually, the valency of nitrogen is 3, valency of oxygen is 2, and valency of fluorine is 1. This is how we understand. So, my dear students, we have calculated the valency for first 10 elements. Now, let's look at the next 11 to 20 elements. Your atomic number 11 is sodium, 12 is magnesium, 13 is aluminum, 14 is silicon, 15 is phosphorus, 16 is sulfur, 17 is chlorine, 18 is argon, 19 is potassium, and 20 is calcium. When we look at the electronic configuration, sodium is 2 at 1 valence electron, magnesium is 2 at 2 valence electron, aluminum is 2 at 3 valence electron, silicon is 2 at 4 valence electron, phosphorus is 2 at 5 valence electron, sulfur is 2 at 6 valence electron, chlorine is 2 at 7 valence electron, argon is 2 at 8 valence electron, potassium is 2 at 8 1 valence electron, and calcium is 2 at 8 2 valence electron. You can now easily find out whether the number of valence electron is greater than or equal to 4, or less than or equal to 4. So, my dear students, if the number of valence electron is less than 4, then the valency is equal to the number of valence electron, and that is why the valency of sodium is 1, valency of magnesium is 2, valency of aluminum is 3, and valency of silicon is 4. You can see here 1, 2, 3, 4 for sodium, magnesium, aluminum, and silicon. Now, my dear students, phosphorus has 5 valence electron, and it is the number of valence electron is more than 4. So the valency is equal to 5 minus 8, and that is why the valency is 3. When it comes to the sulfur, the total valence electrons are 6. So 6 minus 8, it is 2. When it comes to the chlorine, the valency is 1. When it comes to the argon, the valency is 0, because it is an inert gas and all the valence shells are completely filled, and that is why the valency becomes 0. Please once again remember that this negative sign is just the representation, what kind of ions they will form. For example, sulfur will form S minus 2 and Cl will form S minus 1. Actually, their valency of phosphorus is 3, valency of sulfur is 2, and valency of chlorine is 1. Now here, when we look at the potassium, it has electronic configuration 2881, and that is why, which is less than 1. So valency is equal to number of valence electron, and thus the valency of potassium is equal to 1. Same way, my dear students, when it comes to the calcium, the electronic configuration is 2882, and that is why the total number of valence electron is equal to 2, which is less than 4. So valency is equal to number of valence electron, and that is why the valency is going to be 2. So my dear students, looking at this, please remember one more exception here. In the last, from 1 to 10, we have seen one exception, that the helium, which has got 2 electrons, but still its valency is considered to be 0. Here the phosphorus is an element which shows 2 valency, and that is the valency 3 and 5. So phosphorus can make the valency 3 and 5. That is how we understand, and we need to remember it for our answering into the various questions during the exam. Now, my dear students, we want to understand the next activity, which says, or which asks us the question that how does the valency in a period, how does the valency vary in a period on going from left to right? So if you go left to right, suppose we think of the period number 3 and we are going left to right, so we will move from sodium to magnesium to aluminum to silicon to phosphorus to sulfur to chlorine to argon. Let us write their electronic configuration and find out their number of valence electrons. So sodium has got 1, magnesium has got 2, aluminum has got 3, silicon has got 4, phosphorus 5, sulfur 6, chlorine 7, and argon 8. Now from this number of valence electron, we can find out their valency. So valency for sodium 1, magnesium 2, aluminum 3, silicon 4, phosphorus again 3, because 5 minus 8, sulfur 2, chlorine 1, and argon 0. So now we can easily understand that going left to right in a period, valency increases up to 4 and then decreases up to 0. Now, my dear students, we want to understand the next question. How does the valency vary in going down the group? When we go down the group, my dear students, how does the valency vary? So all the elements present in the same group have same number of valence electrons. Thus, all the elements in the same group have same valency. This is the typical situation of the valence electron, that all the elements present in the same group have same number of electrons, and as they have the same number of electrons, they have the same valency. Thus, going down the group, the valency does not change at all. So please remember that going down the group, the valency does not change. Now let's look at the activity number 5.7. Atomic radii of the element of the second period are given below. You can see this period number, second element, boron, beryllium, oxygen, nitrogen, lithium, and carbon. Their atomic radius is given like boron for 81 picometer, beryllium 88 picometer, beryllium 111 picometer, oxygen 66 picometer, nitrogen 74 picometer, lithium 152 picometer, and carbon 77 picometer. Now the question is, arrange them in the decreasing order of their atomic radii. So if we go into the decreasing order, we need to start with the highest and go with the lowest. So when we arrange the atomic radius, 152 is greater than 111 is greater than 88 is greater than 77 is greater than 74 is greater than 66. That is what lithium is greater than beryllium is greater than boron is greater than carbon is greater than nitrogen is greater than oxygen. So this is how we can arrange them in the decreasing order of their atomic radii. Now we have the next question. Are the elements now arranged in the pattern of period in the periodic table? Yes. These elements of period 2, they are actually in the same order in that period, and that is why we can answer yes. These elements are arranged in the pattern of the periodic table. Which element have the largest and smallest atom? So you can see that the atomic radius of lithium is 152 picometer, and that is why the atomic radius of lithium is the largest. Atomic radius of oxygen is 66 picometer, and that is why the atomic radius is the smallest. So we can easily answer that lithium has the largest atom and oxygen has the smallest atom, my dear students. Now, my dear students, we want to study about the atomic size. So, my dear students, अगर आपको अभी तक कुछ समझ में नहीं आया तो आप पूछ सकते हैं, अदरवाइज वी कैन मूव टू स्टडी दी एटॉमिक साइज। आप लोग अपने आप को अनम्यूट करके अगर आपको कुछ समझ में नहीं आया तो पूछ सकते हैं। Let's start to study about the atomic size, my dear students. The term atomic size refers to the radius of an atom. The atomic size may be visualized as the distance between the center of the nucleus and the outermost shell of an isolated atom. Once again, I am going to read the definition of atomic size. Atomic size is the distance between the distance from here you can start the distance between the center of the nucleus and outermost shell of an isolated atom is known as the atomic size. The atomic radius of hydrogen is 37 picometer. Please remember that 1 picometer is equal to 10 to the power minus 12, 10 to the power minus 12 meter. This is power. So please remember that 1 picometer is equal to 10 to the power minus 12 meter. Now the question arises, why does the atomic radius decreases moving left to right in a period? So if you move left to right in a period, why does the atomic radius decreases? We have seen that atomic radius decreases, but why? The atomic radius decreases in moving left to right along a period. This is due to, now we are giving reason, this is due to an increase in the nuclear charge, which tends to pull the electron closer to the nucleus and reduces the size of the atom. See, if you understand this, it's okay. If you don't understand, look at this picture. I have tried to explain you. If you move from left to right, you go from lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So you move in this direction actually. When you look at the picture of these atoms, lithium has got 3 proton, 3 electron, beryllium 4 proton, 4 electron, boron 5 proton, 5 electron, carbon 6 proton, 6 electron, nitrogen 7 proton, 7 electron, oxygen 8 proton, 8 electron, fluorine 9 proton, 9 electron. Now when you move from lithium to beryllium, there is an attraction between 3 proton and 3 electron, 4 proton and 4 electron, 5 proton and 5 electron, 6 proton and 6 electron, 7 proton and 7 electron, 8 proton and 8 electron, 9 proton and 9 electron. So my dear students, more is the number of protons and electrons, more is the force of attraction. So as you move left to right, there will be more force of attraction between the protons and electrons. More is the number of proton, more is the nuclear charge. So as you move from left to right, the nuclear charge increases. Please remember, my dear students, as you move from left to right, the number of protons and electron increases, and that is why the nuclear charge increases. Going lithium to fluorine, nuclear charge increases. That is what now you can easily understand, that going from lithium to fluorine, nuclear charge increases. Now let's look at the answer once again. The atomic radius decreases in moving from left to right along a period. This is due to an increase in the nuclear charge, which tends to pull the electron closer to the nucleus, and thus the atomic size decreases. So now you, from these 3 points, you can understand that going left to right, the nuclear charge increases, and as nuclear charge increases, the force of attraction also increases, and that is why the atomic size decreases. Now, my dear students, we want to study the activity 5.8. Study the variation in the atomic radii of first group elements given below and arrange them in an increasing order. You can see that we have group 3 elements, sorry, we have group 1 elements, they are lithium, sodium, potassium, rubidium and cesium, but they are not arranged in the proper order. So the atomic radius of sodium is 86, lithium 152 picometer, rubidium 244 picometer, cesium 262 picometer and potassium 231 picometer. Now we arrange them in the increasing order of their atomic radius. So 262 is greater than 242 is greater than 231 is greater than 186 is greater than 152. So we can say that the atomic radius of cesium is greater than rubidium is greater than potassium is greater than sodium is greater than lithium. So when you go down the group from lithium to cesium, the atomic radius actually is increasing. Name the element which have the smallest and the largest atom. So you can see here that lithium, my dear students, with the 152 picometer atomic radius is the smallest one, and cesium with the 262 picometer radius is the largest atom. Now, how does the atomic size vary as you go down the group and why? Let us try to understand how does the atomic size vary as you go down the group. First, you look at this picture. You can see that I have shown you the pictures of lithium, sodium, potassium, rubidium and cesium. You can see easily that if you move from lithium to sodium, one new shell. Lithium has got only K shell, sodium has got K and L, potassium has got KLM shell, rubidium has got KLMN shell, cesium has got KLMNO shell. So you can see that the picture itself going bigger and bigger, because each time when you move from one period to another, or each time when you move from one element in the group to the another element in the group, each time one shell has been increased. That means the shell has arranged away from the nucleus. So moving from lithium to cesium, number of shell increases. Now let us see the answer. You just need to remember that as you go down the group, the number of shell increases. So atomic size increases down the group. This is because new shell are being added as we go down the group. You can see that lithium to sodium L shell is added, sodium to potassium M shell is added, potassium to rubidium N shell is added, rubidium to cesium O shell is added. So each time when you move from one element to another, a new shell is added. This increase in the distance between the outermost electron and the nucleus, so that the atomic radius also increases in spite of the increase into the nuclear charge. So as you go down the group, the number of shell increases. So thus the nuclear charge increases, the distance between the nucleus and the outermost shell increases, and that is why we can easily understand that the radius increases. Now, my dear students, we want to study about the metallic and non-metallic properties. So please have a look to this picture. You can see here the picture of the periodic table. You can see that these green colored substances are metals. The yellow color substances are non-metals, and those which are shown with the pink color, they are the metalloids or semi-metals. Please remember that hydrogen is a non-metal which is represented with the yellow color. Please remember that hydrogen is a non-metal which is represented with the yellow color. Okay, fine. Now let's look at the activity. Examine the elements of the third period. See, this is the third period we are talking about. This is the third period. Examine the elements of the third period and classify them as a metal and non-metal. So we just need to classify these elements as a metal and non-metal. Elements of the third period are sodium, you can see here sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. This is what I have written: sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Out of these, the metals are sodium, magnesium and aluminum. You can see that they are represented with the green color, and that is why these three are metals. Phosphorus, sulfur, chlorine and argon, you can see that phosphorus, sulfur, chlorine and argon, they are represented with the yellow color, and that is why they are non-metals. And silicon is a metalloid. You can see here we have the silicon, which is a metalloid. You can see here silicon very easily. So silicon, which is a metalloid in this case. Now please understand, on which side of the periodic table do you find metals? So you can see that on the left side of the periodic table, you find the metals. On which side of the periodic table you find non-metals? So you can see that the non-metals are found into the right side, and that is towards the top. You can see this downer group, or the bottom side again, is filled with the non-metals, but you can see these non-metals on the right side and towards the top end of the periodic table. My dear students, it is very easy for you to understand. Now let us understand the same concept once again with little more details. The metals like sodium and magnesium are towards the left side of the periodic table. You can see that these metals, sodium and magnesium, they are towards the left side of the periodic table. When non-metals like sulfur and chlorine, you can see I have shown you the sulfur and chlorine. This is the sulfur and chlorine. This sulfur and chlorine are found on the right hand side. You can see sulfur and chlorine are found on the right hand side of the periodic table. In the middle we have silicon. You can see this is our silicon. Yes, this is silicon we are talking about. In middle, we have silicon, which is classified as a semi-metal or a metalloid because it exhibits some property of both metals and non-metals. So, my dear students, we have seen that the periodic table has metals on the left hand side, it has non-metals on the right hand side, and in the middle we have the metalloids. These metalloids, my dear students, they are they are present here, and these metalloids actually uh, are the different kind of elements other than the metals and non-metals. Now let us understand about the metalloids in detail. So let us write or let us read the definition of the metalloids. Let's pay attention to the metalloids. Uh, Metalloids, my dear students, in the modern periodic table, a zigzag line separates the metals from the non-metals. The the borderline elements like boron, silicon, germanium, arsenic and antimony and tellurium and polonium are intermediate in the property, and they are called the metalloids or semi-metals. Please pay attention to this periodic table. Here you have the periodic table on your screen, my dear students. From this periodic table, you can see that there are some elements. These elements are boron, silicon, germanium, arsenic, tellurium and polonium. Once again, boron, silicon, germanium, arsenic, tellurium and polonium, they separate these metals from non-metals. These are the non-metals. So these elements which separates metals and non-metals, they are zigzag in manner. You can see that they have the zigzag motion, so they are present in the zigzag way, and they have the properties of both metal as well as non-metal, and that is why these elements are called the metalloids. So please understand, once again I am going to read the definition for you, my dear students, that in the modern periodic table, a zigzag line separates metals from non-metals. The borderline elements like boron, silicon, germanium, arsenic, antimony and tellurium and polonium are the intermediate in property. Intermediate in property means they have property of both metal as well as non-metal and are called the metalloids or semi-metals. So this is how, my dear students, we study about the metalloids. Now I hope you understood everything about metalloids. If you could not understand anything, you can ask me. Now, my dear students, we want to study metal electropositive elements. So we already know that metals are electropositive elements. Metals tend to lose electron. Please remember, metal tends to lose electron while forming the bond, and that is why they are called the they are electropositive in nature. So if we have metal M, it will produce M plus N, and it will lose an electron. So metals are electropositive, and that is why metals make positive ions in most of the cases. So metals are electropositive and they make positive ions, and that is why metals are called electropositive elements. Now we have a question. How do you think the tendency to lose electron will change down the group? So if you go down the group, suppose how this tendency to lose electron changes. So down the group, the effective nuclear charge experienced by the valence electron is decreasing because the outermost electrons are farther away from the nucleus. So my dear students, please remember that if you go down the group, the ability to lose electron increases, and as the ability to lose electron is the ability of metallic character, and that is why going down the group, metallic character increases. Down the group, the effective nuclear charge experienced by the valence electron decreases because the outermost electrons are farther away from the nucleus, and that is how we can say that the tendency to lose electron increases. How will the tendency to lose electron change in a period? So if you go left to the right in a particular period, you can easily understand that as the effective nuclear charge acting on the valence shell electron increases across the period, and that is why, my dear students, the ability to lose electron decreases into the period, my dear students. You can now we can look at the non-metallic characters or non-metals. Non-metals are electron negative. They generally take some electron and then they make negative ions. So if we have non-metal M, this non-metal M will take N electron and will make M minus N. and that is how we can say it makes the negative ions. So they are electronegative in nature. How do you feel the tendency to gain electron? Gain electron means non-metallic character or electronegativity. So how the tendency to gain electron changes as you go from left to right in the period, my dear students? Tendency to gain electron increases as you go left to right across the period. How would the tendency to gain electron changes as you go down the period? So as you go down the period, the tendency to gain electron decreases, my dear students. So if you go down the period, the tendency to gain electron decreases, and if you go left to right the period, the tendency to gain electron increases, my dear students. So whatever the various factors that we have studied, let us summarize them, and we can easily understand the various properties. Here you can see here the various periodic properties is explained in the form of increasing upside arrow and decreasing downside arrow. So going down the group, the atomic radius increases, and going left to right, the atomic radius decreases. Going down the group, electronegativity decreases, and going left to right, electronegativity increases. Going down the group, metallic character increases, and going left to right in the period, metallic character decreases. Going down the group, non-metallic character decreases, whereas going left to right in the period, non-metallic character increases. Ability to make acidic oxide, which is by non-metal, so going down the group, ability to make acidic oxide decreases, and going left to right in the period, ability to make acidic oxide increases. Ability to make basic oxide going down the group increases, and going down the group, ability to make basic oxide decreases, my dear students. In these two slides, my dear students, I have solved all your these are the in-text questions which I have from your textbook, and these are the exercise questions that we have taken from your exercise. So here we have solved all your exercise and in-text question belonging to the all the topics that we have discussed here. I have written it for you, and I have already sent you the uh, PDF file also. Now, my dear students, do you have any doubt? You can ask me if you have any doubt. बच्चों, अगर आपको कुछ पूछना है तो आप लोग मुझसे पूछ सकते हैं. अगर बच्चों आपको कुछ समझ में नहीं आया है तो आप लोग मुझसे पूछ सकते हैं. कुछ पूछना चाहेंगे? क्या आप मुझे सुन पा रहे हैं?
यस सर.
ओके. कुछ नहीं पूछना तो हम ये क्वेश्चन सॉल्व करते हैं. लेट अस सॉल्व दिस क्वेश्चंस. Let us look at the first question, my dear students. How could the modern periodic table remove various anomalies of the Mendeleev's periodic table? So the answer, modern periodic table is based on the atomic number but not atomic mass number. Mendeleev periodic table was based on the atomic mass number. There were some problems, but modern periodic table is based on the atomic number. Second, the position of the isotopes. Isotopes are the element with same atomic number but different atomic mass number. Their atomic mass number were different, so they were not having the same position in the Mendeleev periodic table. But in modern periodic table, isotopes also have the same position, and that is why the anomaly of the Mendeleev's periodic table has been resolved. Now let's look at the second question. What does the second question tells us? Name two elements you would expect to show the chemical reaction similar to the magnesium. What is your basis for your choice? So my dear students, magnesium, the atomic number Z is equal to 12. So my dear students, we have magnesium 282. Same way, if you look at the beryllium, the electronic configuration is 22. If you look at calcium, it is 2882. So both beryllium and calcium have valence electron 2. Magnesium also have the valence electron 2, and that is why they have the same chemical and they have the same valency. The basis of the choice is the same number of valence electron, and that is why we can say that beryllium and calcium would expect to give the same kind of chemical reactions. Now we have the question number 3. Name 3 elements that have single electron in the outermost shell. They are hydrogen, lithium, and sodium, and potassium. You can look into their electronic configuration and you will get idea. 2 elements that have 2 electrons in their outermost shell. Magnesium has 2, beryllium has got 2, calcium has also got 2. Same way, 3 element with the filled outermost shell. So helium, K shell completely filled with 2 electron, argon, K and L. Argon has got K, L and M, all 3 filled, and neon, K and L shells are filled. Lithium, sodium, potassium are the metals that react with water to liberate hydrogen gas. Is there any similarity in the atom of these elements? Yes, these all atoms, lithium, sodium and potassium, have 1 electron in their outermost shell, and this is the similarity among all these elements. Now let's look at the helium is an unreactive gas and neon is a gas of extremely low reactivity. What, if anything, do their common, what do this helium, neon have common? So if you look at the electronic configuration of helium, it has K shell completely filled. If you look at the electronic configuration of neon, it has both K and L shells are completely filled. So they have filled outermost shell is common among them. The modern periodic table, which are the metals among the first 10 elements. So if you write the first 10 elements, they are hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. And out of these 10, lithium and beryllium are the metals. By considering their position in the periodic table, which of these following elements would you expect to have maximum metallic character? Gallium, germanium, arsenic, selenium and beryllium. So beryllium and gallium are expected to be metallic in their nature, but beryllium and gallium, if we compare, gallium is present in the 4th period, so gallium is bigger in size and hence has a greater tendency to lose electron than beryllium, and therefore gallium is the most metallic, gallium is more metallic than beryllium, and maximum metallic character can be seen with the beryllium. Now let's study some of the other questions, my dear students, which may be your exercise questions. So let's have a look to them. Let's have a look to the question number 6 from the exercise. Position of the 3 elements A, B, C in a periodic table are shown. See, look at group number 16 and group number 17. Group number 17 are halogens, and which mostly contains the non-metals. Group number 16 also are mostly non-metals. They are present at the right end of the periodic table, and that is why they are mostly the non-metals. State whether A is more metal